Hi, everyone. I guess we're going to get started here. Welcome to another episode of the Common Lisp Study Group. I'm your host, Ram Baden with Atlanta Functional Programming. Today, we're going to be continuing our exploration of the cl-reactive library. For those of you who are just joining us on this stream in this series of introductory demos to this library that I've been exploring for the last couple of weeks now, just a fair warning. Number one, cl-reactive is currently not available in Quick Lisp. I mentioned this last week for those who watched last week's episode. I recommend you actually look at last week's episode, primarily because there is one issue that I had to fix in last week's episode. And I'll just briefly mention it here for folks who want to use this library immediately. And that is in the functions library for the definition of def signal function. The function base class, well, I may as well just show it to you. The function base class in cl-reactive source functions.lisp, which represents signal functions, originally only was inheriting from signal base. But because it required some callable functionality, specifically access to some functionality that is Lisp dependent, ultimately it has to inherit from CL function. The fix that I came up with was essentially have it inherit from C2mop funcallable standard object. That seemed to have worked to actually go and fix and actually made the rest of the code work flawlessly. So I still haven't actually figured out if this worked on every Lisp out there. I'm pretty sure it will, because cl-reactive is actually a pretty fully functional implementation of the meta object protocol across pretty much every Lisp I've used, and that includes Clojure, CLisp, Allegro, and so forth. So if folks have any particular comments about this particular fix for this library, I have not yet determined whether or not this could be set up as a pull request or not. But please post in the comments, in the YouTube comments, or folks who are on the call who have suggestions. After we go through today's discussion, we can have a little bit of a more deep dive as to some of the things that I've been looking into. And if there are other fixes or better fixes that we could do, we could certainly take a look at it. As I mentioned last week, cl-reactive is a reactive programming library that is almost an alternative to the cells library. Now, recall that cells was class-based, mainly that when you're building models and you're developing this kind of reactive structure, you are leveraging the slot-based mechanisms that are available in the Common Lisp object system to define your formulas, defining your inputs, and specifying your outputs based on some signal change, if not anything else. One thing to mention again there is, in many respects, cells can be thought of conceptually as kind of a way of defining blocks inside of a block diagram. cl-reactive, on the other hand, as I mentioned last week, was at the variable and function level. So it tries to implement the signals mechanism for creating a signal network and change propagation network on top of just normal Lisp functions. And it created a series of macros and functions associated with that. One thing that I wanted to kind of show that I found something interesting is when we gone through quite a few things last week, mainly deferring signals, how to define basic variables and basic signal functions. Our first very basic network that we defined last week, where we just simply set up a simple network with a simple input signal that was a variable that, when changed, will compute automatically using the signal flet, the computed signals for the square and the cube. We also talked about deferring these signals. So what that meant was you would be able to actually catch particular signals and not allow multiple signal updates to occur until you left the scope of a with signals deferred, as we saw here um, uh, in our simple example where we ended up, just going through and figuring out when min and max are ultimately going to be computed. One thing to note, signals will ultimately get computed, especially signal functions, and this is just a review, when they are asked for. So if you asked for, even within a deferred block, for any signals that you thought would be delayed, it will still be computed and you'll end up getting the updated value. It's not that within a signal update deferred that you will not get the updated, most up-to-date value within that block, and it will ignore the signal. It's just that it is lazily waiting until it's out of scope, and all unused signals that are still available within the scope of the function, they will get updated after you left that with signals updates deferred block, as we see here. All right. I noticed one weird thing that, because I thought, last week, oh, because we were able to, use the signals and then def signal function, right? I could ultimately create a closure using signal let that within the scope of the signal let, I'm able to just compute the signal value, get the set signal value, and so forth. So the scope of the signal is only within the block of this signal let. Now, this is actually how def signal function is actually defined. It's a macro that expands, if you see this, into essentially a prog-n that defines a variable that represents the signal, and that signal is ultimately just nothing more than a call to a function that was defined locally within signal flet, and then ultimately a convenience function that that calls cl-reactive on the signal value. But one weird thing occurred when I tried doing this that I learned. So I'm just going to quickly show this example before we move on to today's discussion, and that is, in here, if you end up, calling signal value, x value, which ultimately is our signal, and we have a setf expander here that would define the new value of the signal. And if we look at, square signal for the time being, square signal is now defined as a def signal function within the scope of our package. Even if I go and say call setf on signal x value with my signal 5, right, which will ultimately update the signal, if you actually call square signal, oh, wait, this just suddenly started working. Maybe that was an issue with my, before, I was having trouble before the stream where this was not actually updating the way I expected it to. I rebooted my Lisp image. Maybe that was it. It was a corrupt Lisp image. If you guys see this, sometimes within the scope of the signal, I'm not going to say that I fixed it, or it was an issue with just a reboot, but if you wrote the code this way, I noticed that sometimes the signal function trigger does not get triggered, and I have no idea why. I just, your mileage may vary. This is the first time this actually worked after I actually rebooted my Lisp image, so there's some weirdness there that I'm not going to, get into. Today, we're going to be talking about kind of the rest of what's available inside the signals, the cl-reactive library, particularly functions that allows you to compose signals, functions that allows you to do certain things related to triggering only on particular types of changes. And what I mean by changes is not necessarily a change propagation event, but I'm talking about what's the best way to say it? a value change, all right? If the internal value of the underlying signal, all right, which we can access using signal value, as you saw earlier, if that changes, then you can actually trigger the signal change to occur to update these things. This is one way to, for example, minimize the amount of signals that need to be computed during the runtime of your system. So you don't have what's called a noisy network. You don't have a lot of noise happening around the time of your changes. So it makes it's easier to kind of track when something actually changes, and we'll come up with it. There's one example that I saw in the README that I thought we'd go through a little bit as I understand it. So this way, we can have some discussion on it. Additionally, we're going to also talk about two functions that allow us to create signals as functions of signals. One is actually nothing more than a extension of normal apply, but to cl-reactive signal objects. And the other one is essentially reducing a collection of signals into a single value that's within the context, with the same interface as, or at least as it looks like the same interface as normal CL reduce. One thing I want to start out before I kind of basically give a fair warning on before we get started here is related to the mutability of signals. Up until now, you saw how we are dealing with signals. We are normally just simply defining, either using signal flat or def signal variable, an actual signal value, and additionally with def signal function. But the thing is if you use either of those, you are creating a variable that will have a generalized expander. You can set f it, you can change it. It is not obviously immutable. So, and there's nothing that stops you to actually go and define a signal that works on specific collections. All right. What do I mean by that? You could certainly define a signal like this. I'm not going to put this in the buffer for the time being, but you certainly define a signal called list signal that holds a list of variables. All right, has an initial value or something like this. The problem with this is although list signal certainly will have these values, right, and you can go and change them. Sorry, not list signal. Signal value list signal. Okay. And if we go and set f it, we can certainly set f it with our normal, 1, 2, 3, and get the value back. If you go and try and modify the existing list destructively, so if you use n reverse on this list or what have you, you will end up potentially having some issues, especially if you start leveraging signals with cl-reactive in a multi-threaded application, or even signals, multiple signals in running concurrently inside your Lisp application, Lisp image, because there may be multiple signal functions that are triggered when or reading that particular signal value at the time that you go and destructively modify the actual contents of the signal. So this is, I think, a little bit of a limitation, but it really depends. With good discipline, you can certainly ignore this small limitation with it. So the library can certainly help you at the function and or even if up to the class level, if you wanted to use this inside of a def class or something like that, you can certainly do so. But just be warned that when you're talking about signals in signal variables or signal functions inside cl-reactive, especially those where you are dealing with collections, so the signal itself is holding a collection of contents. just be warned that if you're modifying it destructively, you're going to have this, I would consider it like undefined behavior. It's going to be just very weird. Does that make sense for folks? Okay, let's go through these. So the first thing I wanted to show is talking about signal composition. Okay. Signal composition is basically this idea inside cl-reactive, which allows you to, potentially set up a signal that depends on, one or more signals. Right. One example of this that comes up with signal composition is something called signal count. Right. This is nothing more than a function of, it's nothing more than a function that takes in a signal and returns essentially a signal variable. So I don't even believe this is a macro. So as you can see right here. So what this does is it allows you to, and I think the easiest way to show this to you is probably just look at its signature a little bit more. It takes in nothing more than the actual signal that you want to wrap, and what it does is it returns a signal function that ultimately counts how many times a particular signal gets called. All right. So in this example that we have here, I took the our test basic network example, although certainly I could have updated the other code a little bit more just to like pass in the signal as an argument into the function. But what I then did is I wrapped it inside a with signal values to compute the signal count. All right. So basically, if you look at this example, what we have is a signal let creates an input signal. All right. Recall that signal let basically is like a let block, and signals don't leak out of that let block. Right. With signal values, we'll take that signal. So with signal values, again, this is just a macro that it's a convenience method that will ultimately allow you to not have to explicitly constantly call signal value on every signal that you're dealing with within the scope of a particular block of a code of a particular form. And here what we're doing is we're actually just creating our signal count function that will just grab the input signal. And again, we have our normal with times, and it will just, return how many times this function, this input signal was called. Now, we've seen this before when we actually call this function here that ultimately it's going to collect the number of times this input signal is called, which obviously is going to be 10 since we did a do times on this, and it will go and return that we have 10 times. But one thing to note about this is if we actually wrapped this particular thing with signals update deferred, all right? I at least according to documentation, I found that I found this interesting. It actually said that it will not trigger the number of times that input signal is called, and it will actually ignore all those updates. So I have not yet tried this particular piece out because I saw this earlier, but I thought we'd just go ahead and try it live and see what happens. So what we're going to do is again remember what with signal updates deferred does. With signal updates deferred, we have to go and create a wrapper around here, and then do cl-reactive with signal. Oops, not here. Hold on. Get this right here. Go and do cl-reactive with signals update deferred. Okay. And ultimately, this is going to, let's go ahead and slurp the next guy. So now everything here is with signals update deferred. And count input signals may not actually get the actual triggered signal. All right. So when you run this, it's like I may be doing this wrong. Let's see here. Let's see. It is. Okay, I see what's happening here. It is triggering. Got it. So according to this, if I just simply change this guy, not this one, this guy, to, let's see, actually not do times, one more, this one, with signals update deferred. If I do one more time the same set, so I'm setting it twice in here. I'm expecting it to kind of do it. It should not trigger it. It should only count it to be 10 times still. But we will see what happens. Yes, it only counts it 10 times. So you see here, what's happening behind the scenes is it's only triggering and counting anytime square, cube, and input signal is called. All right. So each time we set it, we're setting it once, but the next time we set it again, it's not actually being counted by the input signal because at this point nothing's being triggered. So this signal is ultimately ignored. This is particularly useful for certain cases where you may want to kind of ignore specific types of updates, and it may require you to, like, just simply, it may be just as simple as just wrapping that particular code with signals update deferred, and you'd be okay. So signal count has its uses. Signal count is obviously a very useful thing for doing some basic benchmarking particularly in terms of figuring out what are your noisy signals. So that way you could do some consolidation potentially with other signals to minimize the amount of propagation events you need to actually handle in order for the network to be stabilized. Otherwise, you'll have a lot of computation happening behind the scenes at potentially every iteration throughout the lifetime of your program. So when you're dealing, this is kind of the same thing that most people who deal with other signaling frameworks, signal slots frameworks like Qt have to deal with, or even WT. There's when you're dealing with signals and the events, you have to go and figure out, you might have a lot of noise, which will cause some unnecessary computation to occur behind the scenes. So this is one way with signals updates deferred in combination with signal count to allow you to go and figure out what are your noisy signals and how you may want to actually go and resolve those to ignore certain computations. Are there questions about signal count? Folks who are on the live stream, also let me know if there's a particular question you want me to take a look at too, and we'll deal with that. The next thing that I was going to talk about is essentially is a way of actually figuring out particular signals and calling other signals based on whether or not a conditional signal is resolved, right? So this is called signal if, all right? Here you might be thinking that I'm going to be, so you have this, example of this conditional signal that could be any sort of condition. It's going to be probably of type Boolean, And what we're doing is we can take in a condition signal and specify either a constant, as I'm doing here, or you can actually specify two other signals that you may want to return based on that signal. So you may want to create, say for example, a sig true, which specifies a value, or of some sort. Okay, and you may want to do the same thing with sig false as well. You can use these two signals to actually go in and generate, sorry, kind of a branching kind of logic when you're dealing with signal if, right? So you could certainly write your code like this, where you have sig true and sig false. What's ultimately returned by signal if is nothing more than a signal function. So if we look at the underlying definition of this, this actually calls def signal. Sorry, not def signal. It will essentially create a signal function using signal flat and return that from the function. And based on the condition, obviously, we can trigger either another signal to be triggered or, just simply return its value. All right. So let's look at an example of this. This is nothing more than using constants, and this might be one way of, specifying something has occurred or not. Right. We have this signal-let for this Boolean signal. And what happens is we have a let block that assigns, essentially using signal if, a variable that holds a signal function that's returned by signal if signal if changes or not. All right, this is pretty simple stuff. And all I'm doing is before changing our underlying signal, I check to make sure that it's set to no, all right? Because obviously, in this case, if you look at the signal if, this is going to be nil, so that should go into the false branch, and then we should get no here. And then, obviously, we should get true if we change the signal here. So if we go and call this guy, you'll see that, as expected, this is just changing between, our true branch and our false branch, okay, or vice versa. And it can be used to potentially trigger particular parts of your network as you are, growing it, as you are designing it. And again, all this is happening at the function level, all right? I can't stress this enough. This is not a class-based implementation. Like there are these macros are allowing you to essentially create normal functions and normal variables. Yes, behind the scenes, you're technically cross classes, but the paradigm that you should be looking for is defining essentially a simple signal network based on input variables and functions that ultimately compute certain types of state based on those input variables. Just give me a moment here to get a sip of water here. And if there are questions, please feel free to ask them. And you can also type them up. I'll hold on a minute here and look at my notes while I'm waiting to. All right. So, triggering only on changes. Looks like there are no questions, so I'm just gonna keep plowing forward here. Now, this is something that I just read up on last night, but I'm still trying to wrap my head around, to be honest. So the idea is, as I mentioned earlier, sometimes based on the nature of how signal networks work, a signal may be triggered to compute its value multiple times, right? This is just the very nature. A signal function will be triggered every time one of its input signals, which may be another signal function or a signal function, signal variable, so anything defined by def signal function or def signal variable. Anytime those are computed, it will go and trigger another one of those child function signal functions that may be dependent upon it to go get computed. But we may not want to compute again because sometimes because of the inputs that are being passed in, it'll end up recomputing the same value. Right? Think about computed properties sometimes that you may have in like databases, like in views, there on a trigger, a particular change will happen, but it'll always end up coming up with the same value. Right? So how can we suppress these signals, right? That's where signal on change is supposed to come in, right? If we look at the actual definition of signal on change, the description of signal on change, it will become somewhat clear, right? Not signal change, signal on change. On change, there we go. If we go and look at the signature of this guy, we can see that it takes in the input signal in question and a couple of additional things. One, a test function to determine when a particular value is the same, right? So sometimes you may have to update this, especially when you're dealing with things that are not equal but EQL. We have to. There's a difference between EQL, equal, and getting the EQ. So just a review of those. I encourage you to go and look back at the hyperspec for more information because sometimes I have to go and review that. But based on what you need, whether or not it's EQ or EQL or equal, you could change this test function, or you could define your own equality function and pass it into the test. The main thing to note about this test function is whether or not it's going to trigger a change. All right, that's what this test function is for. The key function is invoked with the previous value and the current value before the test function is invoked to determine how those two values are equal. All right, so there's two essentially functions here that will determine whether or not whether two values are equal and when two values are equal. Why there's two, I did not quite get. There was an example that I thought we'd go through just to see what might be the issue there, but honestly, I'm still not entirely sure what the difference is about whether and when two values are the same, whether or not something has to be triggered. So let's just check this guy out. Okay, so we have a question here. Is this yes? For folks who are listening in on the Hangout, let me do something for you all because I put this in the description. Let's see. this is, so again, for folks who want to actually look at this library, incline cl-reactive, it's on GitHub. You can clone it and check it out. Let me go back to what this is here. So let's go ahead and grab this example. So this next example, I'm just, the references is from the cl-reactive README. And it's particularly one that I want us to review. Just one thing to note is here, I'm going to have to just change this up just for 1 second. Mainly, this guy has to have this because I'm not using the package. So folks, you don't, if you have a preference on using package, go right ahead and use it. I just am one who tends to like to know what the exported symbols of something is or not. So, all right. So, in this example here, if we let me just change some of this indentation, we are basically defining two signals, all right? And then we've defined a signal function that computes the maximum of the two signals, all right? And what this is doing here is it's going to compute max on change the first time it actually gets called, all right? But the next time that x is set to 50, all right, at least if I understood it correctly, max on change will, signal max changed will not trigger its dependence, even though signal max will get updated. And the main reason is signal max is dependent upon sig x, but signal max change, there's no updates to signal max change until the next time it's called. So ultimately, what ends up happening is that the issue is going to be since we go out of scope, the signal is going to be dropped and it will not get computed. All right. So you can use this in several ways, but again, like I said, in the way I understood signal on change, it sounded awfully similar to what we talked about earlier with signal updates deferred, but it apparently has a much more complete interface in terms of what it's supposed to do. So it might be that I'm missing something here, but the understanding is the network will only get updated when one of the input signal changes if you use signal on change, right? So if the value of the input signal changes internally, then it's going to trigger an update to the actual parent signal and the rest of the children that are dependent upon it. Okay. Let's check this guy out. So if we run this here, what is this? Oh, he's never defined. He's never used. He's defined but never used. So here, let's see if we use this, what happens. Print object. cl-reactive signal value, signal max change. Okay, so let's just see what happens if we do this. Oh, sorry, not that. That's not what I wanted to do. I'm total butterfingers today. Let's print this guy out and let's see what happens. So Yes, there we go. So you can see here, as illustrated by this code, with signal value sigx, when we set f on x, remember this is nothing more than an alias to cl-reactive signal value. When we call set f on x to sigx, that's going to actually trigger the computation of this signal. All right, remember this is an actual signal function computed that will compute the max, right? But signal max changed will not occur, will not change, because the signal max wasn't actually called, so it's almost like a deferred, and it gets computed again. So if we ended up calling this guy, and let's say that we did this, and here, we'll see that signal max change got occurred here. And if we go in and do this, you'll see that signal max didn't actually get computed. It'll recognize that 100 is still the actual one that's been changed. So if we actually ultimately, though, change it to something that's greater than that, right, we will end up seeing that the actual network gets updated accordingly. All right. Finally, one thing that I was going to mention, and this is just quickly on two functions, and I'm still debating as to when this is actually useful. But there's signal apply and then signal reduce. There are these two other functions that I can just quickly go through, and that is creating a signal that's a function of other signals, which is with signal apply. And we could create a simple example of this by just doing, cl-reactive signal let's do sigx, 0 type integer, sig y, 1 type integer, and sig z. So folks who are wondering why I'm actually labeling everything with a type, it's just that I didn't want I don't necessarily want the type t to being there. You could, that means you could put any specific value in there. I think with the type information, it actually does some sort of lenient type checking to make sure that you're not assigning the incorrect value to the signal behind the scenes. Of course, that I haven't actually tested that theory just yet, so that's something that we could certainly look at. And what this is going to do here, but with signal apply, what we do is we can now create a function, signal apply. And what this does is it's going to create a signal function at the end that we could then use. So let's just do, instead of this, let's do let. Okay. Let's call it the sum signal to being nothing more than cl-reactive signal apply. This is an example that I saw earlier, and we specify our three signals, sig y and sig z, and what this does is it just calls normal apply on this and grabs each of the signal values and then computes the final thing, right? Let me do this. There we go. If we go in and call some signal, I think I have to call this using signal value. You end up getting something like this. Okay. And let's call this twice after setting up one of the values to, like, say 5. All right. So, and you will see very quickly that this is doing nothing more than computing the 3 values. Ooh, wait a second. That's interesting. Some signal did not get updated when I called sigx. Okay, that makes sense. It's because of the fact that this is a list again. This goes back to what I was saying earlier about modifying the values of a list. So right now, this is bound to not the list of signals. It looks like it is bound to only one can also take constant. Where did I mess that up? It looks like we're supposed to be able to actually go and modify this. Oh, I'm sorry. I should be using cl-reactive signal value sigx, because I'm not using with signal values to actually get the signal value. I'm actually defining a signal let. That's my mistake. And let's see this now. There we go. So, signal apply is nothing more than one way of actually doing sort of aggregate statistics and aggregate calculations separate from the rest of your thing. You can apply, this is just like any normal function apply, all right? It will actually go in and allow you to look into a specific a specific set of signals and then grab some information out of them. All right. You can also do the same thing if you take this guy and then simply change from signal apply to reduce. And I'm going to just do this very quickly. Apply, reduce. Okay. This should actually be the same signature, but in addition, you can also do some other stuff with reduce, because reduce has obviously, a much more fuller function signature than apply does here. Like with apply, I think you don't get everything. Let me just make sure of this. I didn't see this in signal apply. Yeah, you only get signals type and ultimately the output type of the signal that you're going to be dealing with. Whereas with if you look at cl signal reduce, cl reactive signal reduce, this is more like our normal traditional reduce function. Okay, you have a start value, an end value, whether or not an initial value that you want to compute from. You could specify, the ultimate type of the actual information. This is this should be all familiar to folks who are familiar with cl reduce, because it matches the same signature here. So here, what I could do is I can also provide an initial value too, but I don't think I need one. So let me go ahead and try this one more time. This reduce, yeah, I don't need one, because it's going to what it's going to do is behind the scenes, signal reduce will ultimately at some point through its thing will call reduce, which will ultimately look at the initial value of the type that you're dealing with and compute the information based on the function that you provide. So that's it, honestly, with cl-reactive. cl-reactive itself is it has bare bones primitive library compared to cells in terms of what it offers in terms of functionality is just basic primitives for computing and creating, signal networks, right? In a reactive style, so in a push-based style. But unlike cells, you don't need additional machinery and actually define your models in a particular object-oriented way. You can actually use normal Lisp functions, and as you saw, ultimately those macros just go down to normal Lisp functions, and they will do whatever additional machinery they need to do behind the scenes using the closure mop to actually go and implement the observability that you come to enjoy in both cl-reactive cells and what we saw when we looked at cl-flow as well. Are there questions? And I'm ready to dive into a deeper discussion. Okay, and it looks like our stream is live, but there aren't many viewers watching us on the live stream. So folks who join us later on, please if you're watching the stream later on, and if you have questions, feel free to let me know. Okay, so here's a question here. I got an NST not found trying to run ASDIF test system. Okay, so you're trying to run ASDIF test system on cl-reactive. As far as I know, and I can just show you the directory structure of this guy. cl-reactive doesn't have, it's kind of lacking in terms of tests as far as I can tell. If you actually look at the reactive documentation, it's only source code here. There's these things called -t that I assumed are the tests, but I never actually gone through and dug deep into what this is. So yeah, it looks like these are our tests. Okay, so let's try something here. You said that you tried ASDIF test system and system cl-reactive. Let's see here. Okay, let's see this. Component NST not found. Oh, okay. You may want to actually load the test project because the easiest way to know whether or not something is loaded or not is just by looking at the actual ASDIF file. This is how I normally kind of debug it. And it looks like there's a package here that didn't get loaded when you load cl-reactive. NST. Yeah, let's go and look at that guy. Quick system apropos. It very well could be that NST did not get loaded. Yeah. Let's see if we can grab it. You can actually load this guy. I don't even know what this NST, it looks like a different testing framework. There's so many different testing frameworks, honestly, for I've never used them all, so I'm always interested in seeing newer testing frameworks. So it looks like what you have to do is you have to load NST into your project in order for you to run the tests, as you can see right now. Picking the one is always based on your use case. I personally think some of the ones that I've used, 5 a.m. really nice. 5 a.m. actually includes, I think, also a fuzzing framework. So for those of you who are interested in things like hypothesis testing, it's a really great framework. Prove from Fukamachi, honestly, is just convenient, because if those of you who are using CL project like I am to do project generation, CL project generates, as part of its project template, a proof-based test package. Now you can go in and change the test package in ASD, obviously, to use other other testing frameworks, but it's just, the dependency that he puts in there as part of it. If you're going to end up changing it, go ahead and I think if you delete proof from the test package, you're okay. There's nothing going to cause any havoc when you use project templates with it, with other tests. But I use it because it's there. It's convenient. It's for quick and easy unit tests. With def test, honestly, you can't go. There's nothing better that you use than proof. Honestly, when you end up checking out the NST things, let me know what you think of it. I'm certainly interested in folks giving talks actually on things that they find that I have not tried out myself. It is one of those, there's just so many libraries out there to try out, right? And obviously you want to also do some of your own kind of like projects. So it'll be interesting. So check it out and let me know. Are there other questions? Cool. For folks hanging in the Hangouts, stick around. Those of you who are in our live stream, I hope you enjoyed today's discussion. Next week, I am determining, there is one more reactive framework that I found, but I'm debating whether or not I want it's mature enough for me to actually try out. So if that happens, I will go ahead and post it in the meetup announcements. Those of you who are on the Lisp Discord server, certainly stick around there too, and for announcements, and I'll let you guys know. And I will sign off of the stream, but we can have an ongoing discussion in the Hangouts. So those of you who are interested in, who are members of the Atlanta Functional Programming Meetup, sign in, join the Hangout for the after hours. I'll see you later.